Okay, I hope I'm audible to all students who are attending this lecture of statistical methods for economics. We continue with our lectures on descriptive statistics. Okay, and the books I prefer to follow for my lectures in descriptive statistics, and in fact, the whole course for statistical methods for economics. This is Probability for Statistics and Engineers by J.L. Devor. Mathematics for Economics and Business by S.C. Gupta. Statistics for Economics by Alan Webster. Okay, these are the books, some of the books I prefer to follow for my lectures in statistical methods for economics. Okay. Now, all students can recall that in the previous lecture, we were discussing about some important terminologies like what is the population, what's the sample, what are the various kind of data sets we have. We had looked at the branches of statistics in the previous lecture. We had also looked at the relationship between probability and inferential statistics. We had talked about purpose of sampling in the previous lecture. And we had also looked at the types of sampling like simple random sampling, purposive sampling, and stratified random sampling. Now, in this particular lecture, I intend to discuss histograms as one of the methods or one of the ways of depicting data. Okay, it's a part of data presentation. And first of all, before digging deeper into and drawing or constructing a histogram, let's first of all understand the difference between discrete and continuous variables. So again, students can write the topic histogram. Within that, students can write some important terminologies. Some important terminologies. Okay, so first terminology is what is meant by a discrete variable. What is meant by a discrete variable? So I can write, students can start writing a numerical variable. A numerical variable is said to be discrete. STB means said to be. A numerical variable is said to be discrete if its set of possible values, are either finite or else can be listed in an infinite sequence. So we say that any random variable is said to be discrete if the set of values taken by that random variable are either finite, they are limited in number, or you can list them in an infinite sequence. So basically, students, when we talk about a variable being discrete, you can count the values on fingers. So discrete variable takes values which are countable. Now those countable values can either be finite or they can be infinite, but you can count them. On the other hand, when we talk about continuous variables, so point number 2 is continuous variable. Continuous variable. So I can write that a numerical variable is said to be continuous if its possible values consists of an entire interval on the number line. So when we talk about a variable taking values in a particular interval, that's a continuous variable. For example, I can give one example for discrete. For example, it would be like this. Let's say marks by 5 students. Okay, let's say 15, 25, 30, 35, 40. Now this is a discrete variable. Why? Because you can clearly see that it's finite. You just have 5 values. On the other hand, suppose I talk about marks by 5. Suppose I write it like this. Marks, let's say 0 to 10, 10 to 20, 20 to 30, 30 to 40, 40 to 50, and so on. Here, marks is a continuous variable. Because we now have class intervals. Now, between 0 to 10, if I talk about 0 to 10, there are infinite real numbers between 0 to 10. Okay, between 10 to 20, we again have infinite real numbers. I can break down the interval into infinite points. If I talk about an interval, let's say from 0 to 10, I can break this interval into infinite points. I can't count them. Similarly, 20 to 30, 30 to 40, 40 to 50. So in the second case, you can see that marks is now a continuous variable because it takes values in an interval and you cannot count them. In the first case, marks by 5 students is a discrete variable because it's taking fixed values which are finite. So students should be able to spot the difference between continuous and discrete variable. A variable is said to be discrete if it's easily countable. It can be finite or an infinite sequence, but you can count. On the other hand, a variable is said to be continuous if it takes values in a particular interval on a real number line. And in case of continuous variables, you can't count them because one particular interval can practically be broken into infinite points. Okay, then moving forward, let's look at the third point. So I'm erasing all this off. Within histogram, let's look at the third point. What is meant by frequency? So students can write the frequency of any particular x value is the number of times that value occurs in the data set. So when we talk about frequency, it's giving us the number of times that particular x value is going to occur in the data set. Okay, then what is meant by relative frequency? Remember, frequency captures the number of times a given value is occurring in the data set. Relative frequency, I can write that the relative frequency of a value, the relative frequency of a particular x value, where x is one particular value of the random variable capital X. Okay, the relative frequency of a particular x value is the fraction or the proportion of the time that value occurs. It is a particular proportion or fraction of the times that value occurs. So students can now write the formula. Mathematically, we can say that relative frequency of a value is equal to number of times the value occurs divided by number of observations in the data set. Number of observations in the data set. I will be doing a numerical based on this, where we are going to find the relative frequency, but very simple. Relative frequency is the ratio of the number of times that particular X value occurs divided by the total number of observations in the data set. Okay, so hoping that all students have understood this. Then let's look at constructing a histogram now. So students can first of all write constructing a histogram. Constructing a histogram with equal class widths. Constructing a histogram with equal class widths. Okay, so let's look at an example. So consider the following data. Consider the following data where we are given hypothetically marks, which is my random variable X, and we are given the number of students. Number of students is my frequency denoted by F. Let's say the marks are given by the class intervals from 0 to 10, 10 to 20, 20 to 30, 30 to 40, and 40 to 50. And the number of students are, let's say, hypothetically 5, 10, 15, 20, 25. So my sum of all the frequencies is how much? You can add them up. 75. Okay. Now, how do I make a histogram? So let's look at the diagram for the histogram. Or let's look at the graph. So how do I draw a graph? We have done this in high school as well. On the horizontal axis, we have the marks, which is my random variable, X. And on vertical axis, we have the number of students, which is my frequency. You can choose a scale of your own choice on the y-axis, on the vertical axis. On the horizontal axis, starting from 0, I need to go till 50. So with equal gaps, 10. So these are all equally spaced. Let's say 1 centimeter. Okay. And similarly, students can choose a scale. I think the best is to choose 5 because these are all multiples of 5. So 1 centimeter represents 5 students on the vertical axis. 5, 10, 15, 20, 25. The scale I've chosen is 1 centimeter represents 5 students on the y-axis. Or I can write vertical axis. Now 0 to 10, we can now, all we have to do in histogram is draw rectangles corresponding to that particular frequency. So for 0 to 10, the number of students are 5. For 10 to 20, the number of students are 10. 20 to 30, the number of students are 15. 30 to 40, the number of students are 20. 40 to 50, the number of students are 25. So you can clearly see that this is a histogram. And in this particular case, all my class intervals had equal width. The width of each class interval was how much? The width of each class interval is equal to the upper limit, which I call as L2, minus the lower limit of the class, which I call as L1. You can clearly see 10 minus 0, 20 minus 10, 30 minus 20, 40 minus 30, 50 minus 40. All of them have the same width, which is 10. So these are histograms for class intervals which have equal width. Okay, so I hope students have understood this. Now let's look at how to construct a histogram if your class widths are unequal. So if I erase all this off, students can now write constructing a histogram. Constructing a histogram for continuous data with unequal class widths. With unequal class widths. So we are now going to construct a histogram. We have continuous data, but we have unequal class widths now. Okay, so first of all, let's look at this step by step. So step one. Step one, given the frequencies, calculate the relative frequency. So the frequencies are given to us. We make another column and we calculate relative frequencies using the formula. We calculate relative frequencies using the formula. We have done the formula for relative frequencies. Okay. Remember, I am writing it again. What is relative frequency? Relative frequency is the number of times the value occurs divided by the total number of observations. Divided by the total number of observations. So relative frequency is the frequency of that particular class divided by the total frequency. Okay. And then, so this is step number one. Given the frequencies, we calculate the relative frequency. And now, step two. Calculate the density. Calculate the density for every class interval using the formula. Using the formula, density is equal to relative frequency of the class. Relative frequency is something which I will calculate from step number one. So relative frequency of the class divided by class width. What is class width, guys? The upper limit minus the lower limit. That is going to give me the density. Step three. Plot the class intervals. Plot the class intervals on the horizontal axis and densities on the vertical axis. Plot the class intervals on the horizontal axis, densities on the vertical axis. This gives us, so plot the class intervals on the horizontal axis and densities on the vertical axis using rectangles. Let me make it more clear, using rectangles. This gives us the required histogram. This gives us the required histogram. So I'm revising all the steps and then we are going to do a problem, practice problem. We now have to construct a histogram when we are given class weights which are unequal. So step number 1, we are given the class intervals, we are given the frequencies. We are going to calculate something called relative frequencies. How do I calculate relative frequency? It is the frequency. I can write it is the frequency of that class divided by sum of all frequencies. F is nothing but the number of times the value occurs in that particular class interval divided by total number of observations is summation F, sum of all the frequencies. So F upon summation F gives me the relative frequency. Step number 2, once I've calculated the relative frequencies, I now calculate the density. Density is nothing but the relative frequency of the class divided by the class width. Class width is nothing but the upper limit minus the lower limit. Step number 3, on a graph paper, I'm going to plot the class intervals on the horizontal axis, densities on the vertical axis. I'm going to use rectangles. The height of the rectangle is nothing but the density. And I can say the length and the breadth. When I talk about the length of the rectangle or the height, it's the density. The breadth is nothing but the size of the class interval. I'm going to show this in pictures also. This is going to give us the required histogram. So let's quickly start the numerical now. Erasing all this off, let's look at a numerical. A numerical example of a histogram, a numerical example of constructing a histogram with unequal class intervals. With unequal class intervals. So let's quickly look at a numerical example. Okay, so we are given the following data. Given the following data. We are given the class interval and we are given the frequencies. The class interval is 2 to 4, 4 to 6, 6 to 8, 8 to 12, 12 to 20, 20 to 30. This is my class interval and my frequencies are 9, 15, 5, 9, 8, 2. Okay, so this is the data which is given to us. You can clearly see, guys, the class intervals are unequal. You can see that the first 3 class intervals have a size of or a class width of 2. This one has a class width of 4. This one has a class width of 8. This one has a class width of 10. The class intervals are quite unequal. Step number 1, I calculate the total frequency and the relative frequency. So what is my relative frequency? First of all, guys, when I add up all the frequencies, what do I get? If you add them up, you get, so this is 9, 5, 14, 19, 28, 36, 38. So 48. If you add them up, you get 48. Okay. I hope all students are clear with this. And then how do I calculate relative frequency? The frequency of that particular class divided by the total frequency. gives me the relative frequency. So how much is 9 by 48? You can check out using your calculators. It's 0.1875. On similar lines, we have 15 divided by the total frequency 48, which is 0.3125. 5 divided by 48, which is 0.187, 0.1042. Let me correct myself, 0.1042. Then 9 divided by 48, which is 0.1875. Then 8 divided by 48, which is 0.1667. 2 divided by 48, which is 0.0417. These are all my relative frequencies, and then I can calculate the density. So what is my density? My density is nothing but my relative frequency. Relative frequency divided by the class width. So my relative frequency is 0.1875. What is my class width? 2 to 4? 4 minus 2, which is 2. Comes out as 0.09. Similarly, my relative frequency for the second class is 0.3125. Divided by the class width is again 6 minus 4, 2. Comes out as 0.156. Similarly, 0.1042 divided by 8 minus 6, which is again 2, comes out as 0.052. 0.1875 divided by the class width, which is 12 minus 8, 4, comes out as 0.021. 0.047. Let me correct myself. 0.047. Similarly, 0.1667 divided by 20 minus 12, which is 8, comes out as 0.021. And 0.0417 divided by 30 minus 20, which is 10, comes out as 0.004. These are my densities. Now, guys, what is my job? I now have to plot the class intervals along with the densities. That is going to give me the histogram. So let's do that just for fun. Let me erase. We don't need this now. So I'm erasing this column. We don't need this now. So I'm erasing this as well. What I'm doing now is I'm writing the densities here. Let me write the densities here. So this is 0.094, 0.156, 0.052, 0.047, 0.021. It's quite difficult to plot these decimals, and that too in the online lecture where I'm not having any scale or any instrument to measure. I can only draw a rough kind of a picture. Okay, so how will the graph look like? So let's draw a graph. This is the origin. Again, I have class intervals on the horizontal axis. And I have densities on the vertical axis. Okay, my class intervals go from 2 to 4. So let's say 1 centimeter gap represents a class width of 2. So I can say 2, 4, 6, 8, 10, 12, 14, 16. I think there's going to be a lack of space here. I have to use a bigger horizontal axis. There's going to be a lack of space. So let me start from here. Let the graph start from here. So I can just plot now 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. This suits fine now. I have taken 1 centimeter gap and taken the class intervals from 0 to 30. Okay. And now on the vertical axis, so this is my class interval. On the horizontal axis, I can just write here class interval. And on the vertical axis, we have density. Densities are anyways not exceeding 0.2. So I can just write, let's say 0. I can just take 1 centimeter gap. Let's say this is 0.05. So this is 0.05. Then we have 0.10. And then we have 0.15. And then we have 0.2. So we basically 1 centimeter on the vertical axis represents 0.05. So 0.05, 0.10, 0.15. I'm adding 0.05 every time. So let's plot 2 to 4 is 0.094. 0.094 will be somewhere here. If I make a rectangle, 4 to 6 is 0.156. Somewhere here. 4 to 6. 6 to 8 is 0.052. 8 to 10, 8 to 12. Now the gap is 8 to 12. From 8 to 12, I have 0.047. Now my rectangle is going to go from 8 to 12. From 12 to 20, I have 0.021. 0.021 will be somewhere like here. To 12 to 20. And then 20 to 30, I just have 0.004, very tiny value. I don't know if students are able to see that as well. It's very tiny. It's kind of difficult to, draw this in an online class, but I'm trying my best to draw it as accurately as possible. So this is 0.004. So can you all see the histogram? You can see that now the rectangles have different breadth. Because the class intervals are unequal, rectangles have different breadth. Okay, so I hope students are clear with this. And quickly, the last thing I intend to look at in this particular lecture, shapes of histograms. Shapes of histograms. Okay, so now let's first of all see what is meant by, based on the shape criteria, I can classify my histograms into the following types. Unimodal histogram. I'm also going to show the graphs on the right hand side. So I can just draw a classification here. I can draw the graph here. Okay, so unimodal histograms students can write are those histograms in which there is only a single peak. So unimodal histograms are those histograms in which there is only a single peak. Okay, and so somewhat if I join the midpoints of the rectangle, if I join them, so somewhat like this, if I draw a graph for more clarity, somewhat like this. Suppose this is a random histogram. This is my variable x. This is my frequency. When I join the midpoints of this histogram, I take the midpoints of the rectangle, I join them. So you can see that there is only one single peak. There is only a single peak. So I can now remove the rectangles. The rectangles were just drawn to, make you clear with the concept. If I remove the rectangles, although we have the rectangles, but let me remove them just to make you understand the picture without the rectangles. So you can clearly see now it's literally like a curve now with only one single peak. This is called a unimodal histogram. What is meant by a bimodal histogram? Bimodal histogram. The bimodal histogram is the one that has two different peaks. As the name suggests, bimodal means it has two different peaks. Okay, so for example, a picture like this. You have one peak and then you have another peak. So I can put an arrow and I can write that it has two peaks. This is a bimodal histogram. Okay, and we are not comparing the peaks. If you look at the local region, within the local region, if you see that there's a mountain coming up, there's a peak coming up, it may happen that this peak is smaller. To make it more clear so that there is absolutely no confusion among the students, I can also draw it like this. There is one steep peak and there's one small peak. Now this is a more steep peak. This is a smaller peak, but peaks are peaks. Understand this. Okay, so it's a bimodal histogram. I can write two different peaks. A histogram with two different peaks is called a bimodal histogram. Similarly, on the top, I can erase the first point and I can write multimodal histogram. Multimodal histogram. Is the histogram. Multimodal histogram is the histogram with more than two peaks. So a histogram with more than two peaks will be called a multimodal histogram. Somewhat like this. Again, I have the variable, I have the frequency. This is one peak, this is another peak, this is another peak. So there are three different peaks. Or I can draw multiple peaks. This is a multimodal histogram. Then, based on symmetry, I can also classify the histogram into the following type. If I erase this point off, the fourth point is symmetric histogram. A symmetric histogram, students can write, is that histogram. So I can write it like this, that a histogram is said to be symmetric. A histogram is said to be symmetric if the left half is exactly the mirror image of the right half. If the left half is exactly the mirror image of the right half, then we say that the histogram is symmetric. From the graph, again, students can see this. You can visualize. This is X, this is frequency, a histogram like this. You can see it's a perfectly symmetric histogram. If you look at the peak, this is the peak. The area to the left of the peak is exactly equal to the area to the right of the peak. I can write that both these areas are equal. Both these areas are equal. Or I can say there are mirror images of each other. So I can say that to the left of the peak and to the right of the peak, both the areas are exactly equal. This is called a symmetric histogram. Okay. And then on the top, I can write, based on shapes, I can write the fifth kind, which is called a positively skewed histogram. I will be doing symmetry skewness as a topic later as well in there. But for right now, just to visualize the graph, what is a positively skewed histogram? Positively skewed histogram. So let's look at what is a positively skewed histogram. Students can write that a histogram is positively skewed. A histogram is positively skewed if the right, or I can say the upper tail, if the right or the upper tail is more stretched out, compared to the left or the lower tail. So I can say that a histogram is a positively skewed histogram if the right tail or the upper tail is more stretched out compared to the left or the lower tail. Look at the graph. So I have the variable x, I have the frequencies, somewhat like this. So clearly students can see that this is the right tail. It's more stretched out. And this is the left tail. It's less stretched out relatively. So you should be able to see the left tail and the right tail properly. This is the positively skewed histogram, and the last kind of a histogram based on the shape classification, the sixth type called the negatively skewed histogram. So I can erase this and I can write negatively skewed histogram. So I can say just the opposite, we all know it. A histogram is negatively skewed. A histogram is negatively skewed if the left or the lower tail is more stretched out compared to the right or the upper tail. A picture makes it even more clear. We have the variable x, we have the frequencies. Now we have a longer tail in the left. It's somewhat like this. You can see this is my left tail, more stretched out. This is my right tail, which is relatively less stretched out. Okay, so I'll talk more about skewness. I'll talk more about symmetry in the coming lectures as well. But I hope the students have understood as per the diagram, as per the graph, you can visualize how we can make a positively skewed histogram, negatively skewed histogram, a perfectly symmetric histogram. And based on the peaks, I can classify them as also multimodal, unimodal, and bimodal histogram. Okay. With this, we are majorly done with histograms. We have learned how to plot a histogram with equal class widths, how to plot a histogram with unequal class widths, and we have also looked at the shapes of histogram. Now, in the next lecture, so I stop in this particular lecture. In the next lecture, we are going to start with measures of location. We all have done this if we had statistics or economics at high school. We have learned about mean, arithmetic mean, how to calculate median, how to calculate the mode of the distribution. So these are all the measures of location. I will be covering them again in my statistical methods for economics course for university students. So I will be covering this in the next lecture. I hope all students have enjoyed this particular lecture. Any doubt, you can unmute your mics and ask, or you can call up, or you can always mail me your doubts at divineschooloфeconomics@gmail.com. This is where I stop in this lecture.